So hello, everyone. So I'm going to say a few words on closure models for fluid and plasma turbulence. Really, this is mostly the work of Kunpeng Li, and also Often Bob from Young Show, who is in the room. Kunpeng couldn't make it to the festival, so he's attending some conference for geeks in Singapore. Outside temperature is probably the same, but I would say the inner temperature is probably lower in Singapore. The air conditioning is functioning over there. Anyway, so I mean, the motivation is something you probably all know. I mean, use all kind of codes, especially for fusion, which are time consuming. So, including fluid simulations that Patrick showed this morning. He didn't give numbers, but these days, it's not all cases. So at some point, you would like to use faster codes, so using lower resolutions with some kind of closure schemes representing the high wave numbers. And for larger decisive. Now, in fluid, there are probably millions of simulations and works on this question. In plasma physics, it's much less. At least in the mood of what I'm going to show, it's essentially work by Smith and Hamilton 7 on the Hasegawa-Mima equation, and a few others. In geokinetic, as far as I know, it's mostly Pierre Morel who is in the room, right? It was, I think, hyperdiffusion in Ginkgo, something like that. I should say, in fact, it's not true. I mean, most of simulations with a fluid or gyrokinetic fluid, say, they use diffusion coefficients which are not at the collisional level. They use actually diffusion coefficients which are higher than that. So it means that they are actually doing LES. So the question is, what is the structure, optimum structure of your closure schemes in order to conserve some of the properties of your high wave number? And then this has been around for some time, but the new thing, as you know here or not, is that AI, artificial intelligence, hopefully I can use this jargon, is bringing some new insight in matter, whether in fluid turbulence or plasma physics. So the question, and of course, it turns out that if you want to get started, as Patrick explained this morning, you want to get started with a low-dimensional, low number of fields model, and for this, Hasegawa-Wakatani is kind of a prototype for this kind of exercise. So the idea is just to start with very modest ambitions, that is to use this 2D two-field model and try to elaborate closure for IDF simulations. And then if it works, to use those for more ambitious simulations, three-dimensional, time-dependent, if these are proved. The question is it reliable? Of course, AI will always give you some result. The question is, can you use them reliably? So that's the motivation for this, it is to use very old theory, in particular DIA, to try to constrain the model and also make some predictions that you can compare with the AI results and see whether yes or no they make sense. So I would start with the Hasegawa-Wakatani model. I was hoping that Pierre Guillon would talk about this before me. Apparently my agenda is obsolete, so the answer is, you even say it's antediluvian or and so that we're surprised. Anyway, so we say a few words on this. Then the second part is what can we learn from old DIA and theories in this way. And then I would say some deep learning algorithms. Of course, I'm not at all, as you know, an expert in AI, so hopefully you would be indulgent. So Kunpeng is the guy who actually did this job. And then I will say a few words on the results and lessons we got from this. So this is Hasegawa-Wakatani. I think say 2 words in this. Very simple geometry, Cartesian XYZ. The B field is uniform in D direction. The equations are having one for the density n, another one for the vorticity here, which is essentially the Laplacian of the vorticity. All equations are normalized in the appropriate way, say. Well, we'll not get into the details. The electric potential here plays the same role as the string functions in compressible two-dimensional fluid turbulence. That's not a surprise for you. And this can be seen from the adaptive operator here, which essentially, you can see involves velocity here, which is a cross product between the z vector and the electric gradient. And of course, there are small molecular diffusion coefficients, which may not be the same for density and vorticity. In the whole thing, of course, you have a density gradient, which is drive, and which, of course, introduces some asymmetries. So the gradient is in the x direction, and this produces drift waves which propagate in the y direction. The drive is coming from collisions, so this term here, which is proportionally the same to the difference between phi and m, electric potential and density. If this parameter, which I call adiabatic parameter, is very large, then density equals phi. This is reminiscent of the Boltzmann law. If c is very small, so say 0, then you couple those two equations, and this is, of course, Navier-Stokes for the second one, and the first one is just the density, which behaves as a passive tracer. So that's all you need to know, so we don't remember. And then you run this. This is spectral simulations. I forgot to say we are using the token to decode, which was mentioned this morning. So the references are the same, Yannick, Philippe. So what about LES? LES is just the fact that you are filtering your field. So capital N will be the convolution of your filter G with a density, and the same for potential capital phi, where G is filter. Here, of course, we're going to use something very, very simple, which is just filter in the wave number space. Right. So this is the effect of wave number bigger than the cutoff wave number Kc onto the low wave numbers. See, there are others. And the proposed closure model on the filter field is very simple. Essentially a combination of diffusion and hyperdiffusion. So here will be diffusion, UN hyperdiffusion. This is steady viscosity, this is hyperdiffusion. And there are two processes, which we see are necessary to get agreement between the large size simulations and the DNS. So these are the D and W effect of vorticity and density, and the effect of vorticity of density and vorticity. And of course, here, because we are more or less in fusion, right? You want to predict the particle flux. Yes, you wanted to ask.
A very ignorant one. I don't know anything about the subject. Are you going to motivate the hyperdiffusion, or you are just going to use it for stability of the waves?
Well, you may want to do this, as you say, but here we are going to predict it, right? So it's not necessarily there. Not supposing that. It could be 0.
You are going to predict it from the AI.
Yeah, AI will give you a number, which could be 0, of course.
Sure.
But what I should have told you is that when I put the D naught, right, here, this one could be hyperdiffusion. In some codes, they do that.
Mm-hmm.
But then D naught is very small. So what I was saying that you want to make a prediction in the particle flux, which is a flux across a given magnetic surface. So here, just position in x, which is just density times the x direction of the velocity. So as I was saying, I think our Katani at the moment is really the test bed for all kind of AI exercises we can find for all kind of purposes. As I said, we are in the simplest kind of situation, but other things possible. Some called approximate deconvolution. So this is working in real space, working for this space. And there are closure computed directly by AI. So you're not trying to use a model as it was showing that is on diffusion, hyperdiffusion. I mean, you're asking the AI just to predict the closure. And apparently this has been developed recently for about ++ code. So this is my contribution to the topic of the festival, boundary layers. You will be the only one, I'm correct. That's already something. And apparently they tested it on Adegawara Katani, and now they are currently trying three-dimensional free terms. And this is very recent. That's an example, which is not fantastic, I should say. Showing in blue the spectrum versus wave number for DNS, and the orange is actually the result of the AI. Kind of. And it was also somewhere by a group in Japan. Now, of course, you can also use AI to produce surrogate models.
When you say closer computed directly by AI, it's within a class of models, or
no, I think you train your networks, right, to predict what you should put for.
and then the result is the spectra, or
that's my understanding. I think directly in the practice themselves. So that's my context. Now, frankly speaking, the paper is not very clear. My impression that at the end they're using that to speed up the startup of their code. So it's another deep coding system. So I can discuss about it if you want. So those are actually using AI at all scales, right? So it typically produce surrogate scales, surrogate models, right, to predict the whole thing, so which is much more ambitious. So I think this was presented by Robin Heinemann some 2 or 3 years ago. And I don't remember Robin, the other Robin was actually presented that or not here in the first year. I didn't know. He could talk about it. Now, in the simple model I presented, just diffusion, hyperdiffusion, I mean, of course, it's much better to work in the Fourier space. Right? There, it's kind of suitable to introduce spectral intensities, just, the square of the density, Fourier component, density square, same for potential, K, and the cross correlation between density and potential, which is a complex number. And you can write evolution equation, right? Here, that would be all the linear nonlinear terms, and this corresponds just to the closure. Now, you will notice that I'm not talking about hyperdiffusion anymore, but it's just because in this formulation, all these questions can depend on K, modulus of K, right? So constant would be diffusion, K squared hyperdiffusion, and of course you can pile up higher order terms. So 4 terms essentially, which are all K, and which involve all these technologies. So you will notice that here it's a real part of the system which matters. And that's one major drawback of this closure model, in that, in fact, if you start with a real, just a CK cross correlation that is purely real, it will stay there. Right? So you're losing part of the information, which is the cross phase between density and potential. And this may be a problem, of course, because it is related to transport. Now, remember, we are talking about high K, on the effect of high K on low K. So for very high K, and I will show that, you may have actually hoped, you may hope that, in fact, indeed, there is little transport produced by those small-scale fluctuations. So this may actually make sense. Anyway, so it's, yes.
Are you using a K to the power 4 on the second line, second term on the right?
You mean K to the 4, which would be hyperdiffusion?
No, I mean, you have 1 K to the power 4 in the upper line.
Upper line.
No, the next one.
This one.
No. Yes. But there's something missing in the just below.
Yeah,
no, just below. On the left.
On the left?
No, on the so, second term on the right.
Second term on the right.
Yes, that
you're right. No, it's being divided by K squared. Remember, it's an equation of vorticity. So the whole thing is divided by K squared. Okay? So they may be right. There may be a K squared mistake. That's true. Okay, so what can we learn from old models? So developed a long time ago, I mean, essentially to produce evolution equation of the cross correlation functions. And this is still untractable. So EDQLM is, a terrible word for AD-DAM quasi-normal Markovian model, which is essentially, about simplifying this equation of the cross correlations. So fortunately, these are terrible calculations. Fortunately, they were done by Gang. I think Pat was co-author this one in the 90s. So they are back. These equations, if you look at the paper, are extremely complex. But remember, I'm just interested in the effect of two, say, high wave number P and Q on the low wave number K, such K equals Q plus Q, right? This means that you can just consider a subset of these DA calculations. And by identification with the equation that we're just showing, hopefully with the right K squared, you find that indeed prediction for these 4 coefficients and the cross versus K. So the typical structure of the series is, propagator, which involves essentially frequency broadening. And these questions A, B, C, D are coming from linear, so you know them, from linear analysis, stability, so you know them. And the other quantities are just the spectral intensities to stopping. Okay, so from this already you can see that the structure I was mentioning before happens this term, which does have a K-square, but all the others really look like what you need. Still complicated, but we can continue in the approximations. In fact, high-K turbulence is kind of now the isotope. So this you can see for two simulations at two different values of the adiabatic parameters, showing the frequency, the spectral density at square versus kx, ky. You see, I mean, typically the cutoff wave number would be here, k equals 2. You see that everything that is beyond that is kind of isotope. Yeah.
Don't you need to drive this simulation with some external force?
No, that's not K in turbulence.
Oh, you're studying the
are unstable. There are instabilities, and C, this one is actually giving you the drive, the amplitude, the intensity. So you don't need force. And remember, these are spectral, so boundary conditions. And same for this one. Of course, this is not true at all for low K. At low K, you have all kind of waves on the force, that's it, right? But we don't assume isotopy for these low K structures. So that's kind of convenient. The other thing that is convenient that the ABCD coefficients are very close to 1 or 1 plus K square, which is a drift wave prediction, at least for C larger than 1. And this is an example, you can see, showing AK versus K for given KS. The imaginary part is extremely small, which is related, by the way, in fact, we are ignoring the imaginary part of CK. As long as you don't have this kind of behaviors, and you see the fit, which would be blue here, this kind of blue is the real part of K. And the other thing, the other approximation here is to assume, which is very common, is to assume power law K. This is, of course, the limited back analysis. So E of K is not the kinetic energy. So remember, it's phi K squared. Kinetic energy would be K squared times phi K squared. Goes like some K to minus 2 beta. The frequency bordering term would be just something that goes like K to the alpha. Alpha goes between 1 and 2. We still have to look into the simulations to make some reliable fit of this. Beta we found 3. So this is here, phi K squared versus K. And this up here is K equals 3, which is actually what you expect for direct entropy cascade, which is what we want. So far, so good. And last thing is, if you are in the target, you don't have to do this. But if you do this, then you get completely explicit values of all the coefficients. Right? So, and this is interesting because you find that the limits will be negative. There is an hyperviscosity, which is positive. The diffusion is actually get close to hyperdiffusion. And there are cross diffusion coefficients, which are not only finite, but one is complete, the other one is negative. So that's the prediction from the IA pushed really to the limit in terms of approximations. Just one last thing before moving to AI, that in principle, these diffusion coefficients should depend on the turbulence intensity. That's very clear from the DIA text. The problem is that we have free spectral intensity, right? So this becomes very common. So, by the way, in fluid dynamics, you probably heard of the Smagornsky model. That's the case, right? The turbulent diffusion viscosity, and it depends on the strain tensor, which is itself related to the velocity. So in this case, what we've done is something much simple. I mean, these closure questions depend just directly on the C parameter, the adiabatic parameter. So C, as I was saying, is controlling the drive, so it's controlling the turbulence intensity amplitude. So you would expect, of course, all these diffusion coefficients to depend on the parameter C. And that's what we did. Of course, it would depend also on the density gradient. So it's been fixed all along in these simulations, but hopefully we'll be able also to produce a fit with respect to the density. So here arrives the fan. That's the chapter for the dips. So what did we do for machine learning? So the first thing which is costly is to build the database. So we built a database with direct numerical simulation spec for 512 square. So first, which are done sample to for 6 people. That's how it looks like. I stole this from a paper by Robin Varenne, density fluctuations versus X and Y here, and same for X and Y. We produce this a lot. This is time dependent. We produce this data. Now, the usual procedure, usual so to speak, right, in the community, is to use something called physics-informed neural network. So what is this thing? I mean, the idea is that not only in the loss function, right, not only you minimize about the distance between the data, the run truth, and the predicted values, but also you minimize on the, say, norm of your PDEs. You write your PDEs as a form of operator times field for 0, right? And you minimize the loss function, you minimize the amplitude of this operator. So if you do this, what you're telling the system is that it has to account for the fact that there are underlying partial differential equations which are ruling your system. Otherwise, you get nonsense. And this is called physics-informed. Now, the other advantage, yes.
Is there a way you constrain the sign of your closure coefficient?
You could, but
we don't
do that. But there are, actually, we come back to this. Maybe we should. We come back to that. Anyway, the other advantage of physics-informed is that the partial derivatives are computed by the neural network itself. So it's for free. That's the very important point. Now, we don't do that for 2 reasons. One is, I mean, the accuracy of the, and this is, by the way, called sometimes automatic differentiation. So the accuracy of automatic differentiation is not that good, especially when you move to higher order operators. So that's one thing. And even worse than that, in the back process, right, that you use to when you use a neural network to compute the partial derivatives of your loss function with respect to the parameters, lower parameters, but also the closure terms. And it turns out that the gradient is close to 0, for instance, if the number of layers is too large. So then the learning process stops and you're stuck. So we move to something a little bit more sophisticated, at least for me, it's much more sophisticated. Maybe for me. Okay. But you probably don't see much of this. But anyway, the thing is, we use something called convolutional long short-term memory. So convolutional is just the fact that if you have an image, instead of multiplying your pixel in the neural network by the activation function, you will convolute with neighboring pixels, right? So of course, this introduces complexity in the sense you will have to take how many pixels we can run the pixel interested in both. This is tried and have to pass the two. Anyway, that's the advantage of this is that you can much better way of correlation in space. And then the other part of this is about tracking correlations in time. So the system is able to track some information, as it says, long time scales, short time scales. So which all is all diagram here. Not going to detail all of this. The other thing is that the loss function here is still in the mood of physics-informed. So you're minimizing the norm of your partial differential equations, but it's computed in the Fourier space. And of course, there you have, it's much more costly, but I mean, you have much better accuracy in the computation of this stuff. So this is not entirely the end of the story, for this works too. Because at the end of the training, right, you still have to perform tests to see whether all this is kind of working or not. So for this, you optimize actually your training by comparing after one iteration, or set of iterations, I should say, the flux versus time here. And this is the same for spectra between the high resolution phase, which is the blue curve here. So this is DNS 512 square. I'm doing sorry, how much time? 5 minutes. Okay. The green one is low resolution LES with closure, and the one would be LES no closure. Of course, it's performing very, very poor. So I'm going to move first on this one, but this is a final thing. Wrap up. So the last step is here. Is if you're not satisfied with this comparison, you train again over and over. So at the end, I didn't do the job myself, as I said, but I think it's a lot of time in terms of parameter tuning and stuff. So what do we gain from this? So the model was trained for 5 values of C, so 0.2, 1, 2, 3, and 4. Again, you see the same thing, but this time the spectrum versus KY, flux versus KY. This is blue, the number DNS. Green is LES with closure, and the orange one is LES no closure. So definitely for C equals 1, and it's about the same for all values of C. So it's kind of okay. And then the question is, what do you call the diffusion coefficient, which was the new network found that DNN is positive, which is good. That's positive diffusion. It decays with C, and that makes sense because when you increase C, you find less turbulence. So it makes sense. High diffusion is another story. It's positive there, but you see for low value of C, you find negative high diffusion. Of course, for all these simulations, the sum of this plus this times k squared is positive. So you do find convergence, but I think this is highly problematic to higher resolution case. So as long as you do LES, it's okay. But if you want to use this model for higher k, then I think it's problem. The other part is interesting. If you look at A is positive this time, you find that it is negative for all values of C that we tested. And this is consistent with the old literature, right? That is a prediction by Heitman from Stokes 76, right? But also other papers, many other papers, not using DIA. And this one I also found negative safety for Adila type of questions. So that's kind of, at least for me, very naively, I was kind of happy. I would bet that AI will actually find the right sign of so kind of interesting. And the idea of viscosity is always positive, which would answer the question, I think, and see. Now, before I conclude, the problem, I'm not sure it's a problem, but I think it is the constants. We find that DNW is negative for small c, not that small, but before 0.2, and positive for c larger than 2. So positive is in agreement with the IA. So that's it consistent because the result I showed you was for large. And DW1 is always negative, so also in agreement with the IA. Now, you probably cannot see the numbers, but this one here is 10 times smaller than this one. So, which seems to say that DW is actually kind of small, you could get rid of it. Now, this is opposite to what Osgo did some time ago, which was in the frame, I think, of turbulence spreading, where he was using two-scale DIA. Was factory, where they actually found the reverse. His DNW was significant and DWN was not. I think we discussed already, I guess, but I think that's the one. At the moment, I have no explanation for this, except that, of course, all these diffusion questions depend on the cutoff weight number. And it turns out that this one is the only one that decays like 1/kc squared, kc being the cutoff weight. So kc is true. I'm not sure we could call this larger than 1, but nevertheless, it might be the explanation for this behavior. So it's kind of mystic. So this is the only surprise at the end in this exercise. Just this very fast, we of course tested the model for other values of C, and usually we find it works. So I can happy with this. So conclusion is we use AI to try to compute the closure model for Hasegawa water so very simple model. The model is constrained by the I mean, beyond 6 coefficients, for instance, you would like to introduce partial derivative in y, because this would reestablish information on the cross correlation on the phase cross phase. This is terribly expensive. That's the main problem, I would say, with AI. That you need a lot of data to train them, and every time you add one more coefficient, it's even more expensive. So we do find that this model kind of works for LBS. And in terms of physics, we find that indeed the system finds negative is positive. It finds the cross terms, first of all, they are not small. In principle, you should keep them in this type of closure. And the sign are kind of okay with it. It's just that one of those two, is sometimes 4, is small, and we don't know why. I don't know. And that's it. Thank you for your attention.